In our last video, we discussed vertical and horizontal shifts, a way that we could start with a base or parent function and manipulate it so that we could graph it a little bit more easily, especially than, say, plotting a bunch of points. This video will serve as a continuation of that, a transformations of functions part 2, where we explore some of the other ways in which we can morph a function. In particular, we can reflect it, sort of create a mirror image of it about the x or y axes. We could stretch it or compress it up and down vertically, or we could stretch it and compress it side to side or horizontally. But let's start with reflections. This can be done both about the y-axis and the x-axis. For the y-axis in particular, we can say that the graph of f of negative x is the graph of f of x reflected about the y-axis, reflected about the y-axis. So for instance, we can explore this using the graph of the square root of x. Here in our dashed line, we have our square root of x graph, and when I turn on this second piece here, we can see in green that it overlays the square root of x. Now, f of negative x in terms of the square root of x would be the square root of negative x. And we'll see when I enter in the negative sign here that this will flip the graph over the y-axis. And so if we enter in a negative, we can see that reflection here. And it really does look like a mirror image of the graph that we started with. Again, the black dashed line here representing f of x equal to square root of x, and the green solid line representing f of negative x, or the square root of negative x. These reflecting about the y-axis. We can see similar if we reflect about the x-axis. The only difference is instead of the negative being next to the x, it's going to be out front of the f. In other words, the graph of negative f of x, the graph of negative f of x, is the graph of f of x, but reflected about the x-axis. And we can return to Desmos to observe this here as well. If I move this negative sign from inside the function, right underneath the square root, to out in front of it to give us negative f of x, or the negative square root of x in this case, we'll see that graph flip down below the x-axis. And we can see that here. And so again here, our dashed black line representing f of x equal to the square root of x, and our solid green line representing negative f of x equal to negative square root of x. We can see that being reflected across the x-axis. And so let's try an example. Let's say that this is the graph of f of x. We want to see if we can graph negative f of x. What this means is that we're going to be reflecting all of our points across the x-axis. So we're reflecting about the x-axis. Now intuitively, you can probably get a sense visually of what that's going to look like, right? Something like this. But we can be precise when we do this to say, this means that we're going to take all of the y values, since we're reflecting over the x, this is a vertical reflection, if you will. We're going to take all of the y values and make them negative, right? That's like if we have x and f of x, we now need to transform this to x and negative f of x. And so in other words, if we look at the point negative 2, 4, for instance, we need to multiply our y value from negative 1 in doing this transformation, so negative f of x, giving us negative 2, negative 4. Likewise, the point 0, 0, well, in this case, we don't really have a negative 0, so when it's on the axis itself, it can stay the same. But likewise, the point 2, 4 will be transformed to 2, negative 4. We're going to take the negative f of x, or the negative y value in this case, and plot that instead. So if we plot those 3 points, we've got 0, 0, we have -2, -4, right? This is -2, -4, and we have +2, -4. Then we can use this to graph our parabola. And we connect the dots, and we have a reflection of our original function. And so this graph in blue would represent -f of x and would be our final answer. But there are also a lot more different transformations we can explore. Next, we can look at a vertical stretch or a vertical compression. Here we can say that for function f and real number a, if a is greater than 1, right? So if it's 2, 3, 4, 5.5, 10.328, anything bigger than 1, we'll see that the graph of c times f of x, is the graph of f of x except stretched vertically. So the graph of f of x stretched vertically. And this kind of makes sense when you think about what multiplication does, right? If you multiply something by 2, it's doubling its size. So in this case, it's doubling our graph's height. So if a is greater than 1, the graph of a times f of x is the graph of f of x, but stretched by a factor of a. So by a factor of a. In other words, if we multiply it by 2, we expect to double the height. We multiply it by 3, we expect to triple the height, and so on and so forth. Now, on the other hand, if a is between 0 and 1, so this would be some sort of fraction between 0 and 1, like 1/2 or 1/3 or 1/10, then what we'll notice is that the graph of a times f of x, is the graph of f, so is the graph of f, except compressed by a factor of a, So if we multiply it by half, we can expect the function's height to be cut in half. And so let's use the function of y is equal to x squared to explore this a little bit. We can see here we have x squared being our original function, our parent function in a dashed black line, and then b times x squared in green. Now right now the parameter b is just set to 1, so it's going to look exactly the same as normal, right? 1 times anything is that thing itself. But if we start to move this slider around, then what we'll see is that graph get taller or shorter, depending on whether we move it greater than 1 or less than 1. So if we move it greater, and I move this to the right, we can see that graph get taller and taller, right? And we can see those 2 points shift further and further up. If we instead bring this less than 1 and still greater than 0, then what we'll see is the graph get shorter and shorter. Now, one thing you might be wondering is why aren't we considering when it becomes negative? Why does it stop at 0? And that's again just because we've already accounted for this based on the reflections. When we multiply by a negative, that's going to reflect the graph about the axes, right? So if we did change the bounds on this and allowed it to go to the negative numbers, we'd see that flip around and reflect about the axes. And so if we bring this all the way up to -1, it will represent a perfect mirror image of the parent function we started with. But we can put that back because for now we'll focus just on the stretch or compression and see with a factor of 2, we've doubled all of the points, we've doubled the height of that function, and with a factor of 1/2, we've cut the height in half. And so again, from our original function in the dashed black line of f of x equal to x squared, we can see in green for when a is between 0 and 1, or in this case, a equal to 1/4, our new function, 1/4 f of x, or 1/4 x squared, is shown in green on our graph. And similarly on the right, we also have our original function of f of x equal to x squared in the dashed black line. And then in this case, for a greater than 1, we have our function 4 times f of x, or in other words, 4 times x squared, depicted in green. And we can see that that represents a stretch by a factor of 4. And so let's try an example where we graph the function 2 times f of x based on the graph of f of x shown here. Now you might be wondering what I've meant by saying the graph is stretching by a factor of fill in the blank, by a factor of a. Well, what we mean is that when we have the point x comma f of x, so any of our points on our graph, we're going to take that f of x and multiply that number by whatever factor. So in this case, we have 2. 2 is greater than 1, so we expect that this will stretch our graph. And so we'll take our new coordinates of x times 2 times f of x. And so with the coordinates that were given here, we could look at -1 comma -1, for instance, and transform that by a vertical stretch of a factor of 2, giving us -1 times 2 times -1, or -2. We could look at 0, 0, which with a multiplicative factor, like multiplying by 2, isn't going to change, and so that stays as 0, 0. And then finally look at the point 1 comma 1 and multiply its y value, its f of x, by a factor of 2, giving us 1 comma 1 times 2, or 2. And so graphing our new points here, we have -1, -2. We still have 0, 0, and we have the point 1 comma 2. And then connecting the dots, we'll have something that looks sort of like this. Hopefully you are a better artist than I, but that will at least give us the rough shape. Okay, and we can see that that's taken our original graph in the dashed black line and stretched it up just a little bit. Okay, and in particular, we've taken those y values of each of our points and doubled them. And so this blue graph here will represent 2 times f of x and will be our final answer. And finally, we can take a look at a horizontal stretch or compression. And so for function f and real number b, if b is greater than 1, the graph of f of b times x, right here we're putting it inside the function rather than outside like we did with the vertical stretch, but the graph of f times b of x is the graph of f of x compressed horizontally by a factor of b. And if b lives between 0 and 1, then the graph of f of b of x is the graph of f of x, the graph of f of x stretched horizontally by a factor of b. And so let's explore that with the function of absolute value of x. Okay, again, just like before, the black dashed line represents the parent function, the absolute value of x, and our green line represents the transformation. Now, of course, in this case, since we're multiplying by 1, that green function is identical to the black dashed line. But if we start to move this to the right, maybe make it greater than 1, what we'll see is the graph get compressed from side to side. So looking left to right, we'll see that v get compressed in. And as we do that here, we will indeed see that. If we multiply it by 2, that will be twice as narrow. On the other hand, if we bring that back between 0 and 1, then we'll see that v open up and get wider. So when we have a greater than 1 multiplicative factor for the horizontal, that will compress it and make it narrower. When we have a factor between 0 and 1, it will stretch it and make it wider. And so again, with our original function of f of x equal to absolute value of x in the dashed black line, we can take our transformation in the case where b is between 0 and 1, right, where this is going to stretch the graph horizontally, it's going to get wider. In particular, we have b is equal to 1/4 here, and this function graphed in green is f of 1/4 x, or in other words, the absolute value of 1/4 x. And similarly, on the right-hand side here, we still have f of x equal to the absolute value of x in the black dashed line, except in this case, we have b is greater than 1, causing the graph to be compressed horizontally. In particular, b is equal to 4, so it's compressed by a factor of 4, and this green line is represented by f of 4x, or in other words, the absolute value of 4x. And we can see that reflected on the graph by the fact that this is compressed, that v is getting narrower as we multiply by the factor of 4. So let's look at an example where we have to stretch the graph of f of x by a factor of 1/2 in order to graph the function f of 1/2 x. Now here, sort of like when we did our horizontal shift from our previous video, the parameter 1/2 is acting on the x, it's acting on the input. And so we'll want to act on each of our inputs, each of our x coordinates, to perform the transformation here. And so what we'll need to do is, starting with x comma f of x, we'll need to transform this by taking x divided by c, or in this case, divided by 1/2. This will give us x over 1/2 comma f of x as our new coordinate pair for the graph of the function f of 1/2 x. Now, as you may remember, dividing by a fraction is the same as multiplying by its reciprocal. And so we can actually reframe this to say we can transform x comma f of x by multiplying x by the reciprocal of 1/2, or 2 in this case, giving us 2x comma f of x. And so if we start with our point -1, -1, we can transform this by multiplying that x coordinate by 2. In this case, -1 times 2 is going to give us -2, and then comma -1. We can apply this similarly to the point 0, 0. Of course, in this case, anytime we multiply anything by 0, it's going to still be 0. And so we will have 0, 0 even after the transformation. And then finally, the point 1, 1, when we multiply its x coordinate by 2, that will give us the point 2, 1. And so if we go ahead and plot these, we can find the point -2, 1 right here, the point 0, 0 right here, and the point 2, 1 here. Now, knowing that this follows roughly the same shape, we can use this to connect the dots, and this will give us a rough sketch of f of 1/2 x running through each of these 3 specific points. And so this graph in blue here would be our final answer, f of 1/2 times x. And we can see that it has indeed been stretched out horizontally. It's wider than our original graph in the dashed black line. So now we've discussed all of the different types of transformations. We can shift up and down, we can shift left to right, we can reflect over different axes, we can stretch a graph, we can compress it, we can do that in multiple directions. We have a lot of different tools at our disposal to morph and transform the way one of our parent functions, those like base level graphs, look. And so from here on in our next video, we'll look to see if we can take all of those and put them all together so that given any variation of a function with any type of different parameters involved, we'll be able to graph all of those through using the transformations. I hope you found these helpful though, and hopefully we can at least so far break those transformations down one at a time so that in our next video we'll be able to build them all together. If you do have any questions, as always, don't hesitate to let me know. I'm happy to help. But otherwise, I hope you do have a good rest of your day, and I'll see you in the next video.